Okay, hello, I'm back. So we just finished that big problem showing the parametrization, how when you have four equations and two variables, or sorry, four variables and two equations, you get two parameters, so you just subtract that, but we'll go more in depth about that later. So right now we're going to do another example. So this is example 2. What's chapter 1.1 first of all, which is systems of linear equations. Just so you have some context. Should have added that earlier, but you know, you'll get over it. Anyways, example 2. Describe all solutions to 3x minus y plus 2z equals 6 in parametric form. So here we have a system here. So solution. Our system has 3 variables and 1 equation, and therefore 3 minus 1 equals 2. 2. Let's put this in brackets actually. Therefore, 2 parameters. So to solve for this thing, we're going to say, let's just say x equals s, y equals t, and then to find z, we do 3x minus y plus 2z equals 6, and you plug the parameters in. So 3s minus t plus 2, what's the z, sorry, z equals 6, and you get z equals 6 equals 6 minus 3s plus t over 2. So then going back up here, z equals 1 over 2 times 6 minus, let's just say, t, or negative 3s plus t plus 6. So that's our equation for z. And so this will work for, this will solve the equation no matter what s and t you choose. X is s, y is t, and z is some function of s and t. And it's pretty obvious if you look at this equation how since we derived, it's pretty clear that, you know, when you have 3 unknowns, you have a lot of freedom for how you can solve an equation. Like, you're trying to equal a constant real number, and you have the choice of 3 numbers that vary linearly. So when you have 3 parameters varying linearly, i.e. they're all to the power of 1, you have, in that regime, i.e. linear algebra, that's the regime we're going to be in for the entire course, you will always have this property here that you have 3 variables, 1 equation, 2 parameters. So you have number of variables minus number of equations equals number of parameters. And there may be some situations where you have 2 equations that are actually the same equation, but in that case you really only have 1 equation, but we'll get to that later too. So this should all make sense. If not, leave a comment and I'll try and help you out with that. Okay, let's do so you're gonna find that as you work through all these problems that, oh, just to finish the we could have parameterized it. We could have said y equals s and z equals t and solve for x, or we could have said x equals s and z equals t and solve for y. So there's 3 different parameterization options for that question. Anyways, so try that out on your own, see if it works. If it doesn't work, leave a comment. Okay, so moving forward, there's 3 cases you can get. 3 cases. You can get So since you have linear equations, they're all pretty much straight lines. So let's say you have two lines. So this is a way to make it easier maybe. You have two lines. So here's your graph. You have line 1. Let's say line 1 is this. And line 2 is this. Two straight lines. So if this is equation 1, this is equation 2. This is your axes. So the only solution you're going to get is when the two of them cross. So for this case, you have two equations and you have one unique solution. Okay, and then you have, this is case 1. Case 2, you're going to have let's say you have a line like this and then a parallel line like this. So even if you extend these lines to infinity, they'll never actually cross. So here you have two equations, no solution. This would pretty much mean you have the two equations in your system, equation 1, equation 2, with two variables here, but there's no solution. It'd be like x plus y equals 1, x plus y equals 2. So x plus y can't simultaneously be 1 and 2. So in that case, you get no solution. For a unique solution, you'd have something like y equals 2, x plus y equals 1. So here you solve for x equals -1. You have one unique solution. Okay? So that's an example of, so when the equations are different, when they're different like this, you can solve for one unique solution. Two equations, two variables. Okay, in case 3 will be you have two equations and infinite solutions. This is your parametrized case. In this case, you can have parameters. So you have, let's say you have a line right here, but you have the same line again directly on top of it. So it's intersecting infinitely. Let's say this is two lines on top of each other. So you might have like y equals 2x minus 1 and y equals then you might have like y equals 4x minus 2 over 2 or something like that. Or like 2y equals 4x minus 2. Something like that. So these are the same, these are different, the two. This is the same equation twice, written a different way. So, two equations, infinite solutions. So here if you have like y equals 2x minus 1 and y equals 2x minus 1, let's say you make y equal to t, x will equal t plus 1 over 2. So whatever your t is, that's your y. Whatever your t is, you add 1 to it and divide it by 2 as your x. So that, you can see for any t, you'll get the same line. So you pretty much made a one variable equation. So anyways, that's the three cases for when you have two equations, two unknowns. And we're going to look in general what happens when you have n equations and m unknowns. But that was just a general statement there. Something that you should have learned in like high school. Vectors. Okay. So now we are going to introduce the matrix. So matrix. Going to the matrix. So here's three equations. 3x1 plus 2x2 minus x3 plus x4 equals -1. 2x1 plus 0x2 minus x3 plus 2x4 equals 0. 3x1 plus x2 plus 2x3 plus 5x4 equals 2. So we're going to construct a matrix from these three equations, and a matrix looks like this. So this is another way of representing this. They can go back and forth between these two. So here's a matrix. You're going to have, let me slow the font here. So you're going to take the numbers and just put them in. 2, or 3, 2, -1, 4, -1. 2, you put the zeros in 2, 0, -1, 2, 0, 3, 1, 2, 5, 2. Okay, then you want to close your matrix off. And to show that this is a constant term, you put a line right here. This is like your equal sign. So that's a way of making a matrix. It's just a more efficient way of showing this. So you have your rows here. You see, oh, I mean, you have 4 columns. Right here, here. Then you have one constant. You have 5 columns total. 4 columns here, 1 column here. This is your x1 column, your x2 column, your x3 column, your x4 column, and your constant column. So those are your columns and your rows. This is your equation 1 row. This is your equation 2 row. This is your equation 3 row. So you may wonder why we do this, but it'll become apparent when we start manipulating matrices. You'll see how much easier it is to solve the equations when you're working with a matrix. So this is the matrix representation of the system of equations, and you can go back and forth between the two. So this is called a augmented matrix because it shows it has like the values actually have the order of them have some kind of significance, and there's this line here that shows the constant. That's called the augmented matrix. So then you can make the coefficient matrix. So the coefficient matrix is going to look like this. This is the coefficient matrix. It's just the coefficients. And then here's the constant matrix, which is just a vector. It's going to look like this. So there's your constant matrix. And if I had a pen, I could make it look nicer probably, but you just make it on actual paper. You make the bracket kind of look like fit it properly, and you make them all line up properly. could be like really nice, like I mean, it would be like this, you know, like really tight, but you'd keep the gap between the two large brackets here. So anyways, so that's a matrix. If you're wondering how I erase stuff that stays black, I made color 2 black, which makes the background color behind things when you erase. So I'm pretty OG at MS Paint. Let's change to this one. This is a nice one. So we have a fancy pen now. Okay. Fancy pen. So you can perform elementary operations on a matrix. Elementary operations. Look at that nice writing. Okay, you can do elementary operations, which are elementary operations. You can multiply a row by a constant number. You can swap two rows with each other, or you can add a scalar multiple of a row to another row. These are the 3 elementary operations. So you might say 1 in 2 in no particular order. 3. These are the three elementary operations. So there they are. Actually, usually it's presented like this. Usually it's usually you put in this order. Actually, I forgot there was an order. It's like this usually. So the lowest one is swapping 2 rows. The middle one is multiplying by a number, and the most dramatic one you could say is when you add a scalar multiple of one row to another row. So those are your 3 elementary operations. Okay, so now let's show an example. So we have, here's our system. Say we have x plus 2y equals -2, and then 2x plus y equals 7. Okay, so this is going to go to this matrix here. It's going to be 1, 2, -2. Then 2, 1, 7. And you're going to want to draw the matrix thing around it. So here's what it should look like. There we go. So this is like how it should actually look in your paper. So here we're trying to solve this system of equations using elementary row operations. So here's what you can do. We can subtract. We're trying to get this state of the matrix to solve it. It's solved when you have this in this form: 1, 0, 0, 1, some constant a, some constant b. That's when you've solved your matrix. And this corresponds to saying x equals a, y equals b. So by using these 3 operations, you don't affect the system of equations. You're just modifying them, but it's still the same. The x and y's are the same values, so you're not modifying the essence of the system. So we're going to subtract 2 times row 1 to row 2. So here we're going to have 1, 2, -2, and we're going to do -2 times this one. You can't see my mouse actually. -2 times row 1 plus row 2. So -1. I wish you could see my mouse. That's weird. Oh, you can see it kind of. So -2 plus 2 is 0. -2 times 2 is -4 plus 1 is -3. -2 times -2 is 4 plus 7 is 11. So we can say put an equal sign here. Put another equal sign. Okay, now we're going to do row 2 divided by -3. So you get 1, 2, -2, 0, 1, -11 over 3. Okay, so that's equal to, so now we're going to do -2 times row 2 plus row 1. So we have 0, 1, -11 over 3. I'm going to do -2 times row 2 plus row 1. So we're getting this. -2, you get 0. You get -22 over 3. Or doing -2. So you get 22 over 3 plus -6 over 3. So you get 16 over 3. So there's your solution. You have x equals 16 over 3, y equals -11 over 3. And if you go back and plug it in, you have 16 over 3 minus 22 over 3 is -6 over 3 is -2. So there you go. 2 times 16 over 3 is 32 over 3. Minus 11 is 23. 32 over 3 minus 11 is 21 over 3. 21 divided by 3 is 7. So there you go. That solves it. So this is solved. Linear algebra works when you have linear equations put into an augmented matrix, and you just do the 3 elementary operations but don't mess with the essence of the equations. You can now use this method to solve systems of linear equations. So that's pretty cool. And the reason you do this is because these are really easy to put into a computer. And now you can write software that very easily solves these things. And in a lot of physics and math, and a lot of science in general, computer science like graphics and such like that, you use a butt-ton of matrices, and you can now solve them very easily and quickly by putting them in this form. Or lots of systems of linear equations, I should say. Okay. So what this is pretty much saying is that a sequence of elementary operations performed on a system of linear equations does not affect the original system, so the solutions are the same. That's pretty much what we just showed from that example. Let's do a bigger example now. Example 3. 3x plus 4y plus z equals 1. Here's equation 1. Equation 2. 2x plus 3y equals 0. Equation 3. 4x plus 3y minus z equals -2. So there you go. And let's turn it into a matrix. So put down here actually. Your matrix will be 3, 4, 1, 1, 2, 3, 0, 0, 4, 3, -1, negative 2. There we go. Okay. So now I'll draw the, put this right here, draw the lines. Let me choose like a smaller brush. There we go. So hopefully you can read that. So now we got to do the algorithm on it with elementary operations to get to solve it. So this is going to equal, here we can swap rows 1 and 2. So let me just do that. Swapping rows 1 and 2, you get 2, 3, 0, 0, 3, 4, 1, 1, 4, 3, negative 1, negative 2. So we just swapped these two rows right here. Okay, this is also equal to, now let's do negative 1 times row 1 plus row 2, and negative 2 times row 1 plus row 3. So row 1 stays the same. 2, 3, 0, 0. Get 1, 1, 1, 1, 0, 0. Oh, wait, no, 0, negative 3, negative 1, negative 2. Okay, now we're going to swap back these two rows 1 and 2. So you get 1, 1, 1, 1 to 1. We're also going to do in the same matrix negative 2 times row 2 plus row 1. So because we swapped them, we're adding this to this and putting it here. So 0, 1, negative 2, negative 2, and 0, negative 3, negative 1, negative 2. Okay, so now we have this. We have 2 zeros here, so we're good. Now our new goal is to make zeros here and here. So let's do negative 1 times row 2 plus row 1, and then 3 times row 2 plus row 3. So you get 1, 0, 3, 3, 0, 1, negative 2, negative 2, and then 3 times this plus this one, 0, 0, negative 7, negative 8. There we go. So that, now we have the value of z. So we can divide z, or we can multiply z by 1 over negative 1 over 7, or divide it by negative 7. So we get 0, 0, 1, h over then we could use that to finish off the rest of it. So we get 0. So negative 2 times this plus row 2, or negative 2 times row 3 plus row 2 gives you 16 over 14 minus 14 over 14 gives you 2 over 7. And then negative 3 here, you have negative 24 over 7 plus 21 over 7, so you get 3 over 7. Or negative 3 over 7. With check, and that is indeed the solution. So x is negative 3 over 7, y is 2 over 7, and z is 8 over 7. So here you can see we did only the original 3 elementary row operations, and we solved this series of equations going through this matrix algorithm, and we got these results. And if you plug these back into here, you will see that they do solve it, even though we manipulated the equations in such a way. So that's more validation that the elementary row operations do not affect the fundamental solution to the system of equations, and they're just a useful tool that allows you to convert the matrix to this state where you can now just read the numbers off, like x equals this, y equals this, z equals this. Okay, so that's the end of the examples. Now we can go into problems, and that'll be in a new video. So thanks for watching. Like, subscribe, comment. If you want private tutoring or any questions answered, you can check the link below or leave a comment and I'll try to get back to you. So thank you for watching.